Hi everyone, I'm Lalit and we'll be discussing a few problems based on week 2 lectures. Okay. Can everyone see my screen?
Yes, sir.
Okay.
Yes, sir.
Okay. Fine. So if you have any questions in between, you can just unmute yourself and then ask me directly. Okay. So how was the week 2 lectures? Because this is the week where actual computer vision starts. I mean, was it easy to understand? Okay, there are no responses, I guess.
Good, sir.
Okay,
It was good, sir.
it was good. Okay, great. Fine then. I guess then this tutorial will be pretty easy for you people. Okay. Okay. Can you see the first question? Okay. Yeah, I think you can see. So you are given a point P in projective space. The point is given by 10, 32, 30 and 2, the three elements of a point. Okay. So what is the representation of point P in 2D real space? So before that, can anyone tell what is projective space? I guess that's the first lecture of the week, or we lecture number 5, if I remember correctly. It was mentioned in that. What is projective space? Anyone? Okay. Uh, no answers. Fine. Maybe then I should reveal what is projective space. So projective space in 2 dimensions. So maybe so when I write P2, the 2 means the number of dimensions of projective space. Okay, so when I write P2, it's a projective space in 2 dimensions, and here we are assuming that the space is real space, in the sense all elements are real numbers. Okay. Okay, so what is P2? This is the projective space in 2 dimensions, which was defined as the 3D real space, the usual 3D real space that you see, with the origin removed. Okay, or you have another equivalent representation if you uh, gone through a few lectures more than the lecture number 5. So it can also be represented as R2 union L infinity, where R2 is the 2D real space. This is the 3D real space, and this one is the 2D real space, the usual one. And what is this? Can anyone tell? L infinity, some notation used in the lectures. It's the line at infinity. Okay, so this is what one can say verbally, but what are the what does it mean physically? Why are these two things equivalent? Can anyone tell about that? mean, any answer? Okay. Uh, can anyone tell me what is this? What does this mean? The specific statement R3 minus origin removed. What does this mean?
When we are in like projecting in the projecting space,
Mhm.
since we use the R3 is notation is XY1, so like it would be XYZ. So if we want to put it into P2, then we need to like divide Z, so X divided by Z and Y divided by Z, and 1 it will be. So here the third the third element is 0, so 0 divided by 0 is like not sense, so we remove it.
Okay, okay, that is fine. I mean, okay, that's what projective space means. That's true. But what does this statement mean? This specific statement, this one. That is right. Whatever you said is right. But we would like to interpret it in a, I mean, more meaningful fashion, like the way it was did in the class. So first, if you can tell me whatever is this in the green box, what does this mean? If you don't know about projective spaces, what does this even mean? What is R3?
3D real spacer.
Yeah, 3D real space. So it has dimensions 3. That means it will have 3 elements, right? And then you are trying to remove the origin from that R3 space. So R3 is also a set. From that set, you are removing one element, which is the origin. That's what this specific equation says. Okay, then what does this? Okay, sorry about this. What does the below equation say? This one. What is R2?
Real space added to a set of uh, values from infinity. Okay.
Okay, okay. That set of values belong to what? The line at infinity, right?
Line it.
Okay. So how are both of these equivalent? Someone gave an answer which is actually right. I mean, but it's not that intuitively explained. So if someone else can just rephrase it, then I guess this question will be solved very easily. So does anyone even agree that both of these are equivalent? Both of these uh, sets, the one in the top and this one and the below one, represent the same set P2. Okay, no one agrees, no one disagrees. Okay, so we'll look at it geometrically. So we have some center of projection. If you remember lecture 5, you are given a center of projection there. So I'll call it as O here. Once we have this, can I draw shapes? Okay, even better. And then I'll take a camera, somehow assume that this is the camera plane. Once you have the camera plane, what will I do? I can just take this point and okay. If you're annoyed by my handwriting, then I'm sorry. I'm trying to learn this writing pad, so just bear with me for some time. Okay. So what does this mean? So you have a center of projection from where you have multiple rays coming out, right? And if you have multiple rays coming
Yes, sir.
out, it will intersect at some point on this plane. This plane is infinite, by the way, just for our convenience. This plane extends up to infinity. Okay. So if you have an infinite plane and then you have rays going out from this point O, which I call as origin. So what does this first thing mean? So as someone said that we take projective space, we have elements like x, y, z, which is same as dividing it with the uh, third element. So dividing it by third element always gives us the last element as 1, and there are some other elements which is given by which has some value. Okay, so all these are equivalent. That means all points on this ray are same in the projective space. Do you agree with that?
Yes, sir.
So I take any point on this ray, it is same as representing that whole ray in the projective space. So what is this? So if I fix this plane and only use the points on this plane, it is nothing but R2, right? 2D real space, just written uh, in 3D in three dimensions, but it's ultimately a 2D space which we have embedded in the 3 dimensions. Agreed? So this 2D real space is this one that I'm talking about, x by z, y by z, and 1. And then comes the line at infinity. So what does line at infinity uh, contain?
Contains the origin also, sir.
Line at infinity contains origin. No.
Okay.
Ideal point.
Okay. What is ideal point? What is ideal point? Someone said that. How do you represent an ideal point?
Where the third, like z direction is like z is 0, x y is 0.
Yeah. So I'll just write it as PQ0 just
Pick.
for
Okay.
avoiding confusion. Okay, fine. So you'll have some form PQ0, where the last element is always 0, and you have some finite elements PQ such that both of them, I mean, either of them is not equals to 0. That's all. Okay, what should I say? So both simultaneously cannot be 0. P equals to Q can be there, but both of them cannot be 0 simultaneously because our projective space does not contain the origin. Okay, so given that you have an ideal point, what is the line at infinity? Why is it a line? How do we write lines? Some L transpose, this is capital X equals 0, right? Where X is some point in projective space and L is some line in projective space. Agreed? So if we use the ideal point, that is P comma PQ0, and what is the line at infinity? Can anyone say that? How do you write line at infinity? Okay, it's easy, right? You have to satisfy this equation equals to 0. How will you satisfy it?
0 0 1.
Yeah, 0 0. Yeah, any element, I mean, any scale factor will also be possible, but we take it as 1. So 0 0 1 will always satisfy this ideal point. So all the set of ideal points will satisfy this line. 0, 0, 1. So that means if we include PQ0 such that both P and Q are not equals to 0 together, then this is the and the set of all these points lie on this line at infinity. So once we have this line at infinity, so what does this represent? With R2 we have some values given like this xy1, where x comma y belongs to R, union again another set pq0, where pq also belongs to R, but p and q cannot be 0 simultaneously. Okay, so this is what the second definition of projective space means, projective space in two dimensions. So what is the first definition? The first definition is take the whole 3D space and just remove the origin. Fine. So why do we remove the origin? If you intuitively see here, this origin lies on all the lines that we, or rather all the rays that we have drawn here, right? So if we say that all the points belong, all these points, red points belong to the same, uh, denote the same thing in projective space, then this is something common to all the rays. You cannot disambiguate to which line you should associate this origin, right? So we remove this point from our projective space. This is just an intuitive explanation. And now again, given that this is in R3, we can always scale it by the third dimension, right? So if we have R3 will contain xy1, I mean xyz, which can be written in the form of xy1, and again R3 will also contain pq0 with the same condition. So all these things are contained in R3, apart from the fact that it will also contain p equals to q equals to 0. So we want to remove that part. So the first definition is simply the three-dimensional space with the origin removed. So can you now see that both of them are same?
Yes, sir.
Okay, that's great then. So if you don't have any doubts here, then I guess we can just proceed with the question. So we have a point P in projective space. That means this P, it belongs to projective space P square. What is the representation of point P in 2D real space? Can anyone answer this? Given that we did this discussion, it should be simple.
XY1, sir.
Now what is X, what is Y? How will you convert it to XY1 form?
Divide it by 2.
Divide by 2. Okay, so first we will equivalently write this as 10 by 2, 30 by 2, and 2 by 2. So with this case, I'll just write p hat as the representation into the real space. So it will be 515. Is it fine?
So 515 and 1, no, sir.
This is in 2D space.
2D,
This belongs to R2.
Okay, sir.
So it's as if you are. Okay, where is the point? Yeah, it's as if you are on this plane now. You don't have to specify the third dimension. A question said that you have to specify in 2D real space, so we don't specify the third element as one. That's all. So just a side note that this specific division by third element is not, I mean, it's not necessary that you have to divide by third element. It's just by convention that we use it in a way to make it easy. We can divide by any other element as well and make sure that that division does not lead to the origin. That's all. But by convention, we use it that the third element should be 1. Okay, fine.
So just a confirmation. So in
Yeah.
that origin is there, right, sir? So that is the real world like if we are taking any photo, so that is the real world object, right, sir? So that like based on the
No, no,
light
no, no,
emission.
no, no. Origin
Okay.
is not the object here.
Object. Okay.
What can origin be if it's not the object?
Light
Image.
source, sir.
Light source. Okay, fine. And any other thing that we are interested here in computer vision? What do we try to do in computer vision? Just a high level overview. What do we need for computer vision? If I frame it correctly. We
Image sensor.
Yeah. So camera is our sensor here. So
Okay.
you can just think of this point as the center of projection for the camera.
Okay. So image plane is
Image
acting as an
plane.
image sensor,
Yeah,
right,
yeah.
sir?
Yes. So
So
that's
the
the.
opposite side, the rays are coming. So we can consider origin as our eye if we like take analogies to it.
Sorry, I did not get you.
If we take analogy, so can we consider the origin as our eye?
Yeah, sure. Why not? Yeah.
Okay.
Yeah.
Yes.
So this is just one camera or one eye or one sensor which captures rays. So you might have studied a similar thing called. I mean, it's also a camera. It's the pinhole camera model. The pinhole camera, if you see, there is a one small,
Yes, sir.
infinitesimally small pinhole, right? So all the rays pass through that pinhole, and then
Pin.
image is formed in an inverted fashion on the other side.
Okay. So the pinhole is like the hole is acting as an image plane, right, sir? Like this
Oh, no, no,
rectangle,
no, no.
parallelogram.
Hole is this thing, the origin,
Origin. Okay.
where all the rays converge.
Converge. Okay, sir.
Yeah. And here I'm representing the image plane at the front of the origin. I mean, there in the pinhole, it goes at the back. So
Can we
that's why it's
call it as
Alright.
a focal point, sir? Origin.
origin is not the focal point.
Okay.
Oh, maybe focal point. Yeah, you can say that as focal point. Sorry about that.
Reference to the pinhole camera, sir. So
Yeah, it's the focal point. Okay. So I guess the first question was pretty easy, and since you understood the first one, we can just jump to the second question. But I hope the projective space is clear to some extent what it means.
Yes, sir.
Okay, yeah, that's better.
yes, sir.
I mean, blindly solving questions will not help either of us. So,
Yes, sir.
okay, so this is the second question, which is similar to the first question, but in an opposite sense. So, a possible equivalent representation of a 2D point. So, you're given a 2D point 1 comma 3 in R square or R2, and after projecting onto P2, what can it be? Can anyone say the answer? So, we have some point 1 comma 3 in 2D space. Yeah, can anyone say the answer?
Option B.
Why is, why do you say so?
So if we take like 6 as the like extra thing, so if we divide, then we'll be ending up with 1 3. Yeah.
Yeah, okay, and that's a reverse way of doing it. That's fine, but yeah, that's fine. So if so, any point in now projective space, given that the point we have here, 1 comma 3, it's in R2. Any point in projective space, equivalent point in projective space, is given by k times 131, right? So we add the third dimension 1 here, and then we multiply it by a scaling factor k. So any of these points which satisfy the scaling factor k appropriately gives us the one of the equivalent representation in two-dimensional projective space. So here the answer is B, 6, 18, and 6. Is this clear? It's just the reverse operation that we did for the previous question. So for k equals to 6, our option turns out to be B. Okay, this is fine, right? We'll move on to the next one then. So here's the question. You are given a homography. What is homography?
Homography is a matrix that transforms like the points from one image plane to another image plane.
Okay, that's good. But any other technical description of homography? This is fine, but mathematically more tech, sound description based on the lectures. What does it represent? I mean, some transformation, right? Transformation in which space?
In 3D space, sir?
Uh, are you sure? There are I mean, the size of this matrix given is 3 cross 3, which is fine. But are you sure that we are dealing in 3D space when we talk about homography?
Hmm.
It's projective space. Is it? Yes, no? So we are talking about the projective space here, right? So what is homography? It's a projective transformation. So it takes points in projective space and then transforms it into another projective space. That's all. So it's a projective transformation. That means H transforms from P2 to P2. For this case, we are transforming it from 2D two-dimensional projective space to other two-dimensional projective space. Is this fine?
Yes, sir.
Okay, yeah. So we are given a homography. We need to compute the transformation of dual conic C infinity star. C infinity star, which is nothing but this I dot J transpose plus J dot I transpose under this transformation H. Okay, fine. What is conic? Any simple answer? What is conic? Or whatever you know about conics.
A cone, sir, in a 3D space.
Uh, okay, a cone in a 3D space, which is fine. Not exactly the way it should be defined. So if you remember, I'm just giving you the class 7 or 8 example. So if you have a cone like this, which is uh, open on both the sides, I mean, it extends up to infinity. So it's a two-sided cone instead of the usual ice cream cone that we have.
Yes, sir.
So if you cut a plane like this, if you have a plane like this, what cut does it? What the cut gives you? What it gives you a circle, right?
Yes, sir.
It's a hollow cone, by the way. So the cut gives you a circle. And if you cut a plane like this, what does it give?
An ellipse, sir.
Not ellipse. Here it gives a parabola. If you assume that, okay, so if you assume that this cone is does not extend up to infinity, it just stops here, then it gives you a parabola like this.
Yes, sir.
If you now do it in a way that it's cutting through both of them, then it gives an ellipse. This one is an ellipse. This one is a parabola. This one is a circle. And how can we get hyperbola?
Cutting it at the origin, sir.
Yeah, that's fine. That's one of the way, but in general you can cut it anywhere. And if you have this, then you happen to have like this, right? There's one parabola upside, one
Yes,
parabola
yes,
downside.
yes.
If you just align it properly, you will have the hyperbola. So these are all represented in a single fashion, which is some x transpose Cx equals to 0, where the matrix C is a matrix representing the conic. Okay. So based on the values of C, you will represent the conic, and based on the dimension, you are either in 2 dimensions or 3 dimensions, or even higher. Okay, fine. So we'll come back to the question. So we have the transformation of dual conic disk. Okay. So what is I and what is J? These are all based on the lectures, by the way. Okay, the point I is 1 I 0. The point J is 1 minus I 0. Does anyone remember this? What it's called? Circular points. Am I right? Okay, so these are the circular points, and when you define C infinity star as I into J transpose plus J into I transpose. Okay, what does this look like? What kind of matrix it will be? It will be. Will it be a symmetric matrix?
Yes, sir.
Yeah. So as you can see that we are taking outer product of two vectors. This is one outer product. This is the other outer product. So it will lead us to a symmetric matrix. So now can you tell, given that we have known what is I and J, why it is infinity? These points lie at infinity, right? I comma I and J. These are the points at infinity or ideal point. The third element is 0, right?
Yes, sir.
Yeah. So these lie on the line at infinity. Okay. So if we just try to solve this, which is also given in the class, it turns out to be you have the first two rows as the rows of identity, and the third row is 0. Okay. Fine. So this part is fine. So this is C infinity star. So now we need to compute the transformation of under the homography. So we have the matrix. How do we compute the transformation? Okay, what will be the transformation under an original conic instead of a dual conic? So an original conic has something like this: x transpose Cx equals to 0. So what will be the transformation under homography? I mean, what? How will the C look like when I apply the homography on this? So it's like if I tell that x dash equals hx, you can just, and h is invertible, so x will be h inverse x dash, right? If you try to place it here, h inverse x dash transpose c h inverse x dash. So this is something we used and not a part. Okay, fine. So once we have this, x dash transpose h inverse transpose c h inverse x dash equals to 0. So I'll write c dash, which is the transformed conic, as h inverse transpose c h inverse. Is it fine? This is the transformed conic, but it's the original conic and not the dual conic. How do you represent dual conics? And can anyone tell that? Does anyone remember the diagram that was shown in the class? If you have something like this was represented by x transpose cx equals to 0, and if there is some other, again a similar diagram like this, but if you have now, so if you have multiple lines which are tangent to this, so all these, the whole conic can be represented with this tangent lines, right? These are the tangents to the conic. So if someone remembers it, it turns out to be L transpose C star L equals to 0, where L is a tangent line. How do you represent tangent line? So any tangent line is represented like this: L equals to C into X, tangent to the conic C. So once we have this tangent line, and assuming that C is invertible, we can just write it as, I mean, I just rewrite it here. L is what? So X will be C inverse L, right? C inverse L transpose C into C inverse L, which is L transpose C inverse transpose C into C inverse into L equals 0. So this is what you get: L transpose C inverse transpose L equals to 0. So if you
Sir,
remember, yeah,
sir, I have a small doubt, sir.
yeah,
How is x equal to C inverse into L, sir?
I'm getting it from here, this one. So,
Yes, sir.
so if your line is C into X, which is the
X.
line tangent to the cone,
And L by C, sir. L by C. So you're taking the
what is
C
C?
onto the numerator.
What is C here? C is a matrix, right?
Yes, sir.
L is what? Vector.
Vector. Yes, sir.
X is also vector. So you can't divide vectors, right?
Yeah. Okay. Okay. Okay.
So
Got
here,
it.
okay, yeah. So just to clarify, I'm using this from where I'm getting C inverse X is C inverse L. Okay, fine. Given this, if someone remembers the uh, form of L, form of C, which is given by the diagonal elements are A, C, and F, and it's a symmetric matrix. So given that this is a symmetric matrix, the inverse will also be symmetric, right? So C inverse is also symmetric. So with this we have what? C inverse transpose is equals to C inverse. So what do we have ultimately? Our dual conic C star equals to C inverse. Fine. Given that we have this dual conic, now we need to check how homography affects this dual conic. Okay. So these are all done in class, by the way. There's nothing new out here. So how do we represent dual conic? L transpose C inverse L equals 0. And if you remember the okay, fine. This is fine. So whatever we have for the original conic, the dual conic will just be C inverse of it. So given that we have the transform conic, original conic like this, which is H inverse transpose C into H inverse, H inverse transpose C into H inverse. So our dual conic will be C infinite C dash star is inverse of this, which is H C inverse H transpose, right? So it's just a matrix multiplication now. Uh, so given that we have homography here, this one, and the dual conic. Okay, yeah, fine. So C dash star will be our homography matrix 1 1 0 1 0 1 0 1 1 0 1 0 0 0 0, which is again multiplied by the same matrix. Okay, so you can just multiply this and get the answer. That's all there is to this question. Okay, we then move on to the next question.
Sir, how is this conics and all useful in computer vision, sir?
It's more theoretically involved, but in projective spaces you can define many properties using conics. From there you can understand how transformation affects, I mean how these transformations affect the conics, and based on that you can get to know how the images will be formed given different transformations. So there is a lot of maths involved there. I mean, I don't think this course does the whole maths at this point. It's a introductory course, so we don't do it here. Okay, so we have another question on homography. So we have this homography matrix given H as 210102031. Compute the transform point of intersection of the straight lines given by this. Oh, it's easy, right? What do we do here? So we have two lines. I'm just writing it in a way that we are used to. L transpose x equals to 0, where the first line is given with these elements and the second line is given with these elements. It's just the coefficients out there. How will you compute the point of intersection?
L1 cross L2.
Yeah, it's just the cross product L1 cross L2. And if we do it in the usual way, we take the determinant with the first row given as directions, and the next rows are just the two vectors that we have in our hand, which gives us a vector like this: 9 minus 4 minus 3. So given that we have this vector now, what can we do? So this is the point of intersection. Given the point of intersection and we have a homography, we need to get the transform point, this point transform. Yeah, sorry about that. Okay, so x dash equals hx. So I'll write this as some point x, which is 210102031. Okay, and we get it as 9 minus 4 minus 3. So this leads us to some values: 14, 3 minus 15. So these are the values in projective spaces, right? This also belongs to projective space P2. So if I just want to write it in real space, how can I write it? We just learned it now.
Divide by minus 15.
Yeah, yeah. So your final answer, if they ask in R2, which was the question, they asked it in R2. So we have to just normalize it in that way. Yeah. So this is your final answer. Okay. And okay, we'll do one more interesting question. This.
Sir, will the conic section part is helpful in like future videos or only for that?
To some extent, yeah, but it won't be that much involved.
Okay, sir.
You just need to know the basics. I mean, how are these conics transformed under homographies, and whatever, whatever we, whatever was discussed is, I mean, good enough. No more details more than that is required. Okay, so we have some lengthy question here. Given that we read about this direct linear transform for non-homogeneous equation. So what is homogeneous equation and non-homogeneous equation? Does anyone remember that? Given the context. So for homogeneous equation, the right hand side will be 0. For non-homogeneous equation, you will have some values in the right hand side of the system of equations. Okay. Uh, so we are given that. Okay. So matrix A is formed from the following set of equations. Can anyone tell where these equations landed? How did they come up? What is the question? We are trying to. Okay. So just to clarify that we are trying to estimate homography. So given that we need to estimate homography, I'm using the notation given in the question. So we have that xi prime equals to h into xi, where h is the homography matrix that needs to be estimated, and you are somehow given that these are given to you, that this and this point in the two planes belong to the same 3D point. So these are given to us, and you need to estimate the homography. That's the aim of this question. So given that we need to estimate homography, you get this matrix. Do you remember how do you get this matrix? These H are what? So these are the rows of the homography matrix, right? Given that we have these rows in homography matrix, so these two are same. The left hand side xi prime and hxi prime should be same if you find the correct homography matrix H. That means since you are in projective space, you also need to take care of the scale factor. So how do we take care of the scale factor? We instead take a cross product of the first of the left hand side and the right hand side. So if the cross product is 0, that means what? Both of these xi prime and hxi are in the same direction, right? Do you agree with this point?
Yes, sir.
Okay, fine. So once you have this cross product thing out there, we can actually write, we can get this equation given that we are having homography defined in this way, where h1, h2, h3 are the rows of the homography matrix. Okay, so given this, so we'll get this matrix. I will just try to write it: 0 transpose wi xi transpose. So here xi is xi yi wi, xi prime is xi prime yi prime and wi prime. That's all. So yeah, there is a prime out there in the question. 0 wi xi prime yi prime xi transpose wi prime xi transpose. Okay, someone is joining now. 0 transpose xi prime xi transpose minus yi prime xi transpose xi transpose xi prime, your transpose times h1 h2 h3, this turns out to be 0. I mean, this should be 0 if these two quantities xi prime and hxi prime are in the same direction. So how many equations do you see? So given one xi prime, that means given one pair of the points xi prime, what how many equations do you see? You see there are three equations, right? But how many independent equations do you think they have?
Two.
Why?
The last one is redundant.
How can you say that?
So when we take the first one and the first row and second row, like if we add that, then that's WI term will cancel, and then we'll be ending up with the
Yeah.
last one.
Okay. So if you actually multiply the first row with xi prime, second row with yi prime, so you get a scaled version of the third row, which is wi prime times the third row. That means they are linearly dependent. So only two of these rows are linearly independent. So we just generally consider the two rows in our case. So for every point, you have two equations. So for every point, you have two equations. Is it fine? So for so if you have n points, small n points, you have two n equations. That means two n rows. What about the columns? So we are given in the question that yeah, we are having non-homogeneous equation. For non-homogeneous equation, this the last element h33 should be 1, right? Do you remember that we fix the last
Yes, sir.
element to fix the scale of the homography? So once we fix the scale of the homography, so you have something here in the right hand side, and you just have 8 elements over here. So you have in total 2n cross 8, uh, the matrix A will have 2n cross 8 the dimension will be 2n cross 8. And where is this matrix A coming from? This is how it was defined in the question here. So here it is that AH equals to 0, but that 0 won't be there since we are dealing with non-homogeneous equations. So it will be something of this form: AH equals to B. So the dimension of A is 2n cross 8, and this is 8 cross 1, and this will be 2n cross 1. The dimensions are fine, right? And we assume that we have full rank matrix, otherwise we won't get mm, I mean we'll have degenerate solutions out there. So what is the rank then if we have it full rank? The If A has full rank, what will be the rank of A? Full rank, but what's the maximum rank that A can take? Minimum of number of rows or number of columns. Okay, so minimum is 2n cross 8. How many minimum number of points do you need?
3,
Why 3?
4.
Why 4? How many parameters you need to solve?
8.
So for 8 parameters, how many equations you need at least?
16
Why?
2n equations.
Why? If you have 8 parameters, you need 8 equations, right? 8 equations means how many number of points?
Okay, 2n is 8, so n is 4.
Yeah, so you need 4 points at least
Okay,
to solve
okay.
this. To solve this equation, 4 points are needed at least. Are needed. So this counting argument is fine, right? So you need 4 points at least. So n can be greater than equals to 4 if you really want to solve it, and it should be full rank so that you can solve it properly, else you won't have unique solution. So full rank means the rank of this matrix A should be 8. So given that this is the case, which one is the correct option? B, right? Dimension of A is 2n cross 8 and dimension of H is 8 cross 1. Okay, so the other part is if the origin of the plane lies on the vanishing line. Okay, so what does it even mean? Let us use some shapes. Okay, so we have some plane out here whose origin is given as 0 comma 0, and then with this you are transforming it to some other plane using the homography, right? Uh, so with homography you might have transformed it in this manner, which has some other origin place at some other place that we don't need to denote here. So our question asks if the origin of the plane lies on the vanishing line, no solution exists. Is it true or not? Okay. So this is the original space. I'll just write original plane. This is the transform plane. So if you have these two given, and if your vanishing line, let it be like this, you have vanishing line going through that origin. Okay. Then what? Then the question that's asked is, okay, does there no solution to this system of equation, or is there a unique solution to the system of equation? Can anyone tell that? Any guesses? So what does this vanishing line mean here? What does this vanishing line mean here? That means in some in this transform space you have parallel lines, right? So the parallel lines, so for every point in the vanishing uh, line you have parallel lines, uh, at least two parallel lines in the transform plane. Is that clear given the definition of vanishing line?
Yes, sir.
Okay, so in the transform so in the transform space, okay, so first we'll look at the original space, not the transform space. Fine. So how is this origin defined in the original space? In P2 we'll write it as 001, right? Do you agree with that? So your two coordinates are 0, we just add the third coordinate to be 1 in the original space, in the original plane, so that we are in now projective space. So given this, our original origin in the original space is given like this, and we now try to transform it. So once we transform it, what will it look like? Hx naught, right? That's a simple equation here. But once this is transformed, what will be this? I mean, these corresponds to the uh, what do you say? The parallel lines. So the parallel lines meet at infinity, at the line at infinity, right? So this transform point also satisfies this line at infinity, right? Because what does homography do? It just transforms one point to the one point in a given plane to some other point in the transform plane, right? So we have transformed this original point which lies on the vanishing line. We are transforming here the origin, not any point on the vanishing line, we are transforming the origin to some other point which lies on the line at infinity. Why? Because this specific point origin lies on the vanishing line. Since this line is on the vanishing line, there exists some parallel lines associated in the transform plane which meets at infinity. So given that we know this, our equation should be satisfied like this, right? This is line at infinity should satisfy the transform point, which is nothing but what? How does line at infinity look like? I mean, how is it represented?
PQ0.
Line at infinity. All those points satisfying this is the these are the ideal points. PQ0, whatever you said. What is this line at infinity? How does it look?
001.
Yeah, 0, 0, 1. So given that we have this L at infinity at 0, 0, 1, x naught as what? Again 0, 0, 1, right? So if you place this here, 0, 0, 1, so I'll just write out the elements. What does it lead to? It leads to h33 equals 0, right? So this one picks up the last row, and this one picks up the last column in the last row, which leads us to h33 equals 0. So do you think you can solve it?
No, sir.
Why?
Because at least one equation should be like not non-zero.
No, not that way. We assumed something in this homogeneous, non-homogeneous equation, right? What did we assume? This is our assumption. This is our assumption, if you remember, that we fix the last element as 1. But if you have a condition that your vanishing line passes through the origin in the original plane, then what happens? Your last element will be 0, right? So if you're
Yes,
already
so
fixing some,
it's always the last element as zero or any element that is zero, sir. Like
so here by convention we are taking as last element as
last element. So since it is zero, so we cannot solve.
yeah. So as I
Yes.
told earlier, that the third we are all considering the third dimension to make it projective space, right? We are adding one to
Scale.
the third dimension. So here
Yes,
it
sir.
turns out to be the last element. So
Last
with
element.
so
Okay.
with that convention, the last element turns out to be 0.
Zero.
Given this thing and given our assumption that the last element should be 1, it contradicts. So we cannot solve it.
Yes, sir.
So the answer to this question is this one. No solution exists, right? I guess this question is clear.
Yes, sir.
Okay, then I guess we can stop the session for now. Thank you for joining. The video and the notes will be available like the way it was done last week. Okay. Okay. Thank you all.